Hello. This lesson discusses physics in pictures. This is just a picture gallery of some of the large instruments that are used to make progress in this fundamental field. The pictures themselves come from a competition held and with the results recorded on the web. And it happened over more than 1 year. This first picture is of a so-called wire chamber, which is recording the tracks of particles, and we can look at the description, which is given by this 2010 global competition, and it comes from DESI, which is an accelerator, uh, which we will actually it has several accelerators, but DESI is a laboratory, and this is the type of if you look at a physics experiment, it consists of many such devices because these tiny particles collide in the center of the apparatus, and then they produce other particles that stream out and have to be detected. They're typically detected, say, in this wire chamber by the electrical charges deposited as the charged particles go through this particular device. This device will not detect neutral particles, just charged particles. Other devices, so-called calorimeters, detect neutral particles. This is a very pretty picture, and in fact, the commentary says it's sort of humorous. The sort of grinning magnets. These are the electromagnetic coils of so-called quadrupole magnets, which are the heart of an accelerator. They bend the particles. Particles go round and round in circles. You saw pictures of that with the CERN accelerator. And here's two quadrupoles being joined together. The particles go in this pipe in the middle, and the electromagnetic um, forces are created in these coils. And there's this, it's the same competition as the previous picture. Didn't win quite as big a prize, but it's pretty. I would say this is a pretty amusing picture, and it is an example of the of what it takes to do an experiment. Enormous amounts of work are necessary. Physics graduate students spend years building this type of thing. Here is a more classical picture, a so-called control room. You have control rooms from lots of things, from various military things, NASA spacecraft, and electrical grids and things like that. And it is, of course, what is controlling the operation of the accelerator. The physicists are sitting in so-called experimental halls where particles are diverted or coming from the accelerator, um, do their thing, they collide, and the physicists in the halls look at the results. But there is back in this control room, there are the key people who keep those particles running around in circles. Well, actually, not the particles that collide. The particles that collide disappear. But most of the particles don't collide, and they keep running around in circles. And every now and then, many times a second, they collide either with themselves, that's when you have colliding rings, or with a fixed target. Here is a picture of the yeah, this is a picture of the ring at Hera. Hera is an electron um, proton accelerator, and it actually is slightly unusual. Most of these rings are either collide protons with antiprotons or electrons with positrons. And this one actually collides electrons with protons, so-called EP collisions. Um, and they do that with having a common tunnel. That tunnel accelerates electrons and accelerates protons. Protons are harder to bend, So you need higher performance magnets. So the magnets used for the protons are superconducting. The magnets used for the electrons, which are not accelerated to as high an energy, are conventional. So here a tunnel is pretty long, 6.3 kilometers. And like the sun one we saw, it has multiple experimental halls, which are pretty big. And this explains here this key idea that you must have, because of protons and electrons have different mass, you need to treat them in different ways. I should point out electrons are very hard to run around in circles because you can't really you have to be very careful because they radiate light. In fact, that concept is used to produce light sources. And when they radiate light, they lose energy. Protons do not do that. This only happens for light particles like electrons. Here is a picture of the so-called relativistic heavy ion collider. That's the Brookhaven lab, which is in Long Island, north of New York. And this has, looking at all of these actually are doing different physics. This is the physics of large fat nuclei colliding with targets. And that can produce interesting effects because as the nuclei are themselves made up of lots of protons and neutrons, and if you really bang them at high momentum or velocity into a target, those you get some sort of relativistic plasma of ions, which puts them into a different state where all sorts of interesting things can happen. So this is REAC is again a big accelerator. It's not quite as big as before, only 2.4 miles in circumference, but it's still a major undertaking. And this again shows you these typical tunnels with the rings which hold the magnets, which then guide the particles around these circles. And these particles, of course, go round and around many times, gaining a little bit of energy each time they go around the circle. Here's actually a totally different type of big science apparatus. This is an apparatus living inside a mountain, and it's the so-called Gran Sasso National Laboratory, an Italian facility. And why would you put apparati in places like that? You also put them at the North and South Pole for similar reasons. And there's a big experiment called Ice Cube that does that. And you do that because if you there are certain experiments involving, in this case, usually particles like neutrinos. And if you take a neutrino, it's very weakly interacting. So if you stick a mountain in front of a neutrino, nothing much happens. However, if you put a mountain in front of a neutron or a cosmic ray and things like that, the junk that lives in the atmosphere, that mountain will stop those neutrons and cosmic rays. So if you put a experimental apparatus deep underground, you get a very clean environment without much background. You have to choose the place you put it so there is very little radioactive contamination. If the rocks of your mountain have lots of radioactivity, it itself will generate its own background. So this is carefully designed not to do that. That's explained in this overlay here. Again, this is a huge facility, 900 scientists, 29 countries, 15 experiments. And it's not surprising if it's the Gran Sasso laboratory, it's on the Gran Sasso mountain. And this explains here that this rock that lives over the experiment, which gives her a huge reduction of a factor of 1,000,000 in the background. And that's pretty important because neutrinos, which is a typical thing we're trying to study, have very low interactions. And so any background is very serious because the background typically is a much more aggressively interacting particles. Protons and neutrons have lots of interactions. Cosmic rays, which are essentially those particles, have those types of interactions. And so you're just going to be dominated even by a small amount of background material. And as we search for the source of dark energy and the curious properties of astrophysics, this type of experiment is on the interface between particle physics and astrophysics. And as it says here, you're looking at the results of supernova explosions, neutrinos produced in the sun, and things like that. And it's a very, very important type of science. And I say it's all done inside this tunnel, which is actually holds a freeway, but they've just burrowed out some physics laboratories by the side of the freeway. And that's just a small sketch of some of the major apparatus that is required to do big science. And one of the reasons I actually left this field was just a huge number of people. When I did particle physics experiments, we only had 30 people on the experiment, and that was, I found, quite a lot. As we noted today, they have 3,000 people on some experiments. So this is the features, which has pluses and minuses of big science. So that's the end of this picture gallery. We'll get on to some more technology in the next unit. Thank you very much.